So we're going to do optics with lenses. This is a converging lens, so we'll start out with converging lenses. Right, and so that means it's thicker in the middle than at the ends, and so it causes rays to converge that come through it. We'll draw all the optics happening at the center lines. That's why I just put dotted lines for the surface. We'll say this has a focal length of 10 centimeters. And so this is the focal point here, and another focal point. The distance to that is the focal length. We will put an object, let's say I put an object at a distance of 20 centimeters, so I'll try to do this to scale. And so an object would be out here, that would be 20 centimeters, and I'll make it maybe 5 centimeters tall. How about like that tall? Right? And so now we're just going to kind of draw principal rays and show what happens to, use this to determine where the image is. And so I can just write a few things down here. First of all, the distance from the object to the lens is called the object distance. And we give that the letter S, right? And so I may be drawing over that here in a minute. And so we can drawing-wise, we can find the where the image is going to be by drawing what's called principal rays. And so the first principal ray is, again, this is for converging lenses. So a ray parallel to the optic axis, like this one, is bent through the focal point on the other side. And so that's that point right there. And so I just do that. And I say, yeah, this ray is going out like that. The second principal ray, 2. A ray through the center is undeflected, and so I may have to make a couple of marks to get this one right. So I want to draw it from the top of the arrow. Eee. Like that. Somewhere like here. Let me get those so that they cross good. All right. So this is ray number 1. This is ray number 2. And then ray number 3. A ray through the focal point on the object side, and I kind of erased that one, didn't I? So I got to draw that back in. Oh, it's 10 centimeters. There's 0. It's going to be right about there. Somewhere in there, I think. And so now I draw this ray maybe that. And now I have to draw it parallel to the optic axis, so it's going to be something like that. And it's not the best drawing in the world, but you can sort of see that these three rays tell you that the object distance is somewhere in here, I would say. And so what we get for that, if I measure it, is about 20 centimeters. We call that S prime, or the image distance. And so it turns out the thin lens equation works for this, and so I can solve this with the thin lens equation arithmetically or algebraically. I can say, look, 1 over the focal length. I'm really running low on juice in these guys. 1 over the focal length is 1 over the object distance plus 1 over the image distance. This equation works for lenses and mirrors, diverging or converging. And so if we're looking for the image distance, we can say 1 over S prime is equal to 1 over F minus 1 over S. And you can see that that would be, in this case, 1 over 10 centimeters, because that was my focal length. That's this distance, right? Minus 1 over 20 centimeters. Right, 1 over 10 is the same thing as 2 over 20. So 2 over 20 minus 1 over 20 is 1 over 20. And so S prime is equal to 20 centimeters. So you can, if you write this height as the object height, and this guy here is the image height, you can see some similar triangles here, and so I'll try to sketch them out just gently in blue. And so there's a right triangle here that includes the object, the optic axis, and the ray that goes through the center, right? If you look at that triangle, it's got a right angle here, and I want to draw your attention to this angle. And then let's look at this triangle over here, right? And you can see that that's a right angle also, and I'll draw your attention to this angle. Notice that these two angles have to be the same, because that straight line and that straight line cross each other, and opposite angles of crossing lines are equal. And so these two triangles have the equal angles in all sides, because if two of the angles are equal, the third one has to be equal. And so what that means is it gives us some information about the ratios of the sides of these things. Similar triangles are equal. And so what that means is that this side to that side is equal to this side to that side. And so y prime over y is equal to S prime over S. And the only change I make to this is that I want to view this as upside down, because y is going the other way, and I'm going to call both the object and the image distance, in this case, positive. So I'm going to say technically y prime over y is minus S prime over S, because I want to view an upside down height as negative. This is the thing we call the magnification. The ratio of the image height divided by the object height is the magnification. If this is much bigger, then I have a high magnification. If this is much smaller than this guy, I have a small magnification. And so this ratio tells me, this equality tells me that if I know the object and image distance, the object distance and the image distance, I can calculate the magnification. Then if I know the height of the object, that lets me calculate the height of the image. And so I've already learned that S prime is equal to 20 centimeters, and S is what we started with, was 20 centimeters. I said that at the start. So the magnification is minus S prime over S, and so that's equal to -1. In other words, the image height is the same as the object height, but it's inverted. Right. So I believe when we started I said that height was 5 centimeters, but let me just measure it again. Yep. And so I can say this is y equals 5 centimeters. And of course, since y prime over y equals minus S prime over S, which is -1, that's what we just calculated, y prime is equal to minus y, and so y prime is equal to minus 5 centimeters. And that's pretty much what we measure when we see this. This is about 5 centimeters tall, and it's upside down. So let's do another one that's not quite as symmetric. Okay, so we're going to do a similar problem. Once again, I still have a converging lens. I still have a focal length of 10 centimeters, which I measured with my ruler, right? I have an object that's height is 5 centimeters again, except now I've picked an object distance of 30 centimeters instead of 20 centimeters. And I'm going to draw all my principal rays again, right? So I'm going to take this guy and run him right along here and have a ray parallel to the optic axis. Right? And then we're going to go so a ray parallel, this is our ray 1, right? You can check the last slide. A ray parallel to the optic axis, a principal ray gets bent through the focal point on the opposite side. And so now I can say, I can look at for a ray through the center, and hopefully I can draw that. It's going to take me a couple of tries here, but roughly speaking, that's where the ray is, right? And so I can kind of do that. Right, and you can see these two guys go off like that. And then finally a ray through the focal point on this side. So that was ray 2, right? A ray through the center is undeflected. And then finally a ray through the focal point on this side, if I can do that right, is bent parallel to the optic axis. So maybe something like that. Like that. And you can see all those rays cross at a single point. Just like the last image, this is a real image because all the rays are actually converging at a point. We'll see a virtual image, right? So this is a real image. If we put a piece of paper there, those rays would be hitting a piece of paper, right? And so I can draw my object here somewhere like this, right? And so if I use my ruler, I can measure my object height, which is about, I get about my object distance. This isn't going to be right because I'm drawing it, but it's about 16 centimeters. That's my S prime, right? And my image height is about maybe 2.6, 2.7. Something like that. And so we can calculate all this thing, right? This gives me a magnification of a little less than 2. Sorry, a little less than 0.5, a little more than 0.5. It's 2.7 over 5. It's a little more than a half. So we can calculate this thing, right? Now we can do the corresponding calculation. We can say, look, 1 over S plus 1 over S prime is equal to 1 over F, or 1 over S prime, which is the thing we were looking for, is 1 over F minus 1 over S. which is equal to 1 over 10 centimeters minus 1 over 30 centimeters. If we want to do that in our head, 1 over 10 is the same thing as 3 over 30. 3 over 30 minus 1 over 30 is 2 over 30. And so S prime is 15 centimeters. We got 16. That's pretty good for a drawing, right? And so this would say y prime over y is equal to minus S prime over S, which is equal to minus 15 centimeters over 30 centimeters, which is minus 0.5. And that means y prime is equal to minus 0.5 times y. This is the magnification, by the way, the thing we calculated just a minute ago, right? Minus 0.5 times y, which is minus 0.5 times 5 centimeters, which is 2.5 centimeters with a minus sign in front of it. We measured about 2.7. That's a pretty good drawing. By the way, the argument that I made on the last screen, which says that, I was picking out, if you just follow this ray, right? Maybe I should be drawing that one in blue. I don't know, right? If you follow this ray, you can make a triangle here, and you can make a triangle here, right? And these are similar triangles. These two angles have to be equal because they're two lines that are crossing, and opposite angles for crossing lines are equal. These two both have right angles where the object is standing vertical, and then that forces the last angle to be equal. That means the corresponding sides are equal, which gives us the equality of these ratios. And so that's where this relationship comes from. And so that's two examples of producing a real image with a converging lens. So now we're going to use a converging lens as a magnifying glass, and I'm just going to draw us another ray tracing area here. So let's do this. Right, I'm going to have a converging lens, and so I'll just draw a lens here with a 10 centimeter focal length, just because that seems to be convenient for this size. And the way you get a lens to act as a magnifier is you put the object, again, this is a converging lens, so technically my lens looks like this, but I just treat it as a straight line, right? If you put the object inside the focal length, again, for this lens, the focal length is 10 centimeters. And so let's put the object at 6 centimeters. How about that? Or something a little even easier. How about let's put an object at 5 centimeters. So if I get halfway between these 2 points, it would be right there. And I'll put a 5 centimeter tall object at that point. And so let me just see if I can do that. Right. So here's my object. It's 5 centimeters tall. And now I'm going to use principal rays again to determine where my object, where my image is. And so this gives me a y is equal to 5 centimeters. This gives me my object distance is 5 centimeters also. Right? I don't think that'll create any unnecessary complications. And so, again, I'm just going to draw principal rays just like I did last time. Here I draw a parallel ray, and we already know that a parallel ray gets bent through the optic axis, right? And so, bent through the focal point, sorry. And so this ray goes off in that direction, right? Similarly, a ray through the center gets bent, it gets undeflected. And so this would be ray number 2. So this would be ray number 1, this would be ray number 2. And finally, a ray through the focal point on this side gets bent parallel, right? In the same way that if this ray was going through the focal point on this side and gets parallel, if a ray was coming from this way and hit, it would get bent parallel. And so since we can't have a ray leave the tip and go through the focal point, what we say is, well, this ray is going to get, is going to leave as though it leaves the tip as though it had come from the direction of the focal point. And so it comes from this direction, if you follow me. And then it gets bent parallel to the optic axis, just like it should, right? And so this is ray number 3, and it comes off this way. And if we look at this picture, we say, well, right away, well, these rays aren't actually going to cross and produce an image. And so what happens here? Well, what happens here is that your eye looks at all the rays coming off this tip that go to your eye. Now, obviously, these rays don't all go to your eye, but some do. And your eye traces those back to where it thinks they would meet. Your eye doesn't actually know where the rays originally came from. It just knows the direction they're coming from when they hit your eye. And so what your eye does is it says, well, this ray was coming from this direction. Let me do a little better job with that, right? This ray was coming from this direction. This ray was coming from this direction. Right. And once again, they all sort of meet right there, somewhere in the vicinity of the focal point right there. Right. And so this is what you see. So this is y prime. This distance here is s prime. And so we can actually measure these guys. This is obviously about 10 centimeters since it occurred right about the focal distance. It's difficult to tell. That looks like it's about twice as big as y, but I can just measure it, right? And sure enough, I get that's about 10 centimeters. And so, by the way, the same triangles occur here just like they did last time. If I look at the ray that's going through the center, I have a triangle here from the object, and I have a triangle here from the image. And once again, these are similar triangles. They both have the same angle here. This guy has a right angle, this guy has a right angle, and that angle has to be equal to that angle. And so these ratios, where the magnification is y prime over y, which is minus s prime over s, still holds. And so I'm going to do these calculations we did a minute ago. I'm going to say, look, 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. And that means 1 over the image distance is equal to 1 over the focal length minus 1 over the object distance, which is 1 over 10 centimeters minus 1 over 5 centimeters, which is 1 over 10 centimeters minus 2 over 10, or just minus 1 over 10 centimeters. And so this gives us s prime is minus 10 centimeters. And so, so the image distance, instead of being on this side of the glass where it would be positive, it's on this side. S prime is, if s prime is less than 0, so the image distance is negative when the image is on the opposite side of the glass from the outgoing ray. Clearly, when the object is here, the outgoing rays, as they go through the glass, are on this side, right? But the image is on this side. And so we call the image distance negative when the image is on the other side from the outgoing rays. This is a virtual image. Because you have to look through the glass to see the image. There's no place to put a sheet of paper and get the image to appear. There are actually no rays crossing back here. That's just a perception. So we call this a virtual image. It's not a real image. Your eyes perceive the image to be there. but it's not actually there. So that was, so the magnification is minus S prime over S. That's equal to minus 10 centimeters over 5 centimeters, right? Because S prime was minus 10 centimeters, and the magnification is minus S prime over S. And so that's equal to 2. The magnification is 2. In other words, this is twice as big as that. The magnification is also equal to Y prime over Y. And so Y prime is equal to the magnification times Y, which is 2 times 5 centimeters, which is 10 centimeters. So the image is upright and virtual and about twice as big as the object. So now we're going to look at diverging lenses. Diverging lenses have negative focal lengths, and they cause rays to diverge. So a diverging lens, this is not a very good drawing, but it's thinner in the middle than it is at the ends. By the way, you know, this is a diverging lens, a lens shaped like this, but also a lens shaped like this is diverging. Eyeglasses are often shaped like this if you're nearsighted. They're thinner in the middle than at the end. I know these aren't very smooth, regular shapes, but it doesn't have to be concave on both sides. It just has to be thinner in the middle than at the ends to give you a diverging effect. And so, so we're going to draw principal rays for this lens again, and they're a little different than they are for a converging lens. So for a diverging lens cause rays to diverge, and so a ray parallel to the optic axis, when it leaves, we would call this ray our principal ray 1. They leave as though they come from the focal point on the other side, right? So a converging lens, let me just put a few dots on there, right? A converging lens takes a ray parallel to the optic axis and bends it through the focal point on the other side. So a diverging lens So, if that makes sense, a diverging lens refracts the ray coming parallel to the optic axis in a direction as though it came from the focal point on the object side. And so that's what a diverging lens does, right? So our ray number 2 is through the middle, just like with converging lenses. For diverging lenses, the ray through the middle is undeflected. Finally, and this one's a little trickier, so this is ray number 2. Let me number it in red. This is number 2. So we're going to kind of do the reverse of this one. So we're going to say, look, a ray aimed at the focal point on the other side. Are you with me? So I'm saying, look, a ray leaving this guy as though it were coming at the focal point on this side. Are you with me? So it's just like, notice if I reverse this ray, it looks like it's going right at the focal point on the other side of the lens, right? Instead it gets refracted parallel. That's what this guy does. He's aimed at this side, and so instead of going in that direction when it goes through, it gets bent parallel. Goes out like this. And so this is ray 3. This was 2. And so let me just write this guy down. 3. Is refracted parallel to the optic axis, since that was our ray 3. Well, this is kind of similar to the magnifying glass version in that none of these rays clearly aren't going to converge to form an image. And so what we have to do instead is say, okay, there's an eye back here looking at this thing, and where does it see these rays converge to? Well, you can already see that these two guys, 1 and 2, appear to cross right about here, and if I draw the third one in there, it'll look like it was coming from that direction as well. And so what this is telling me is that my image is right there. And so I would say my, if I just measure this in centimeters, I'm going to say my S prime is 6 centimeters, and my height is about 2 centimeters. Y prime is 2 centimeters. And I don't think I started by giving the data, so let's just measure both of these again, in case I didn't mention them earlier. So my original object distance, S here, is 15 centimeters. That's what my object distance is. And my object height is 5 centimeters, so Y equals 5 centimeters. And so we should be able to check these numbers by doing our little calculation with our focal length and stuff like that. So I'm going to erase these guys really quickly here. Maybe not as quickly as I'd like. Right. And so I'll say, I just go back to my regular equation. 1 over F is equal to 1 over S plus 1 over S prime. And so 1 over S prime is equal to 1 over F minus 1 over S, right? And well, so that means that 1 over S prime is equal to 1 over minus 10 centimeters minus 1 over 15 centimeters. I don't know what that is. Common denominator for those guys is 60. This is, no. Yes? 30. This is 3 over 30, negative 3 over 30, so it's minus 3 over 30 centimeters, minus 2 over 30 centimeters, over 30 centimeters, which is minus 5 over 30 centimeters. And so S prime is 6 centimeters. That's what we got here, right? Except minus. Except minus. And so I'll have to put a little minus sign on this side because the image is on the opposite side from the outgoing ray. The outgoing ray is here, and so if my image is on the other side from the outgoing ray, my image distance has to be negative. And that's what that's what this gives me. It gives me a negative image distance, and then I can say my magnification is minus S prime over S, which is minus 6 centimeters over 15 centimeters, which is 0.2, right? 6 over 15 is the same thing as 2 over 5, so it's not 0.2, it's 0.4. There we go. And that's equal to Y prime over Y, and so Y prime is equal to 0.4 times Y, which is equal to 0.4 times 5 centimeters, which is 2 centimeters. And that's what we measured when we calculated it. Once again, I keep drawing these triangles that are similar these relationships are justified by the fact that this triangle and this triangle are similar triangles. They'll always be similar triangles for all these mirrors and lenses that we do, and so these relationships hold for all of those guys.